Welcome, learning, growing mathematicians. I'm here to talk to you today about one of the most basic things we do with vectors, and that is we deal with the dot product of vectors. It's basically the way of multiplying two vectors that you will encounter, and we use it in a lot of different applications and a lot of different situations and different formulas. So first thing I want to do is just show you what the formula is for a dot product and how that works. So here's that definition of the dot product. It says if V is equal to A sub 1 times I plus B sub 1 times J, and W is A sub 2 times I plus B sub 2 times J, if those are vectors, then the dot product of V and W is defined as follows. And basically, you are multiplying in order the coefficients. So A sub 1 times A sub 2, and then plus, and we move on to the coefficients of J. So first we multiply the coefficients of I, then we multiply the coefficients of J. And you can think of that as multiplying the horizontal components and then the vertical components, and we are adding after we do that. Let's look at what that looks like in component form. If I were to say, in terms of component form, that I have a vector, let's say, U1, U2, and sorry you're hearing my dog in the background, that's vector U. And then I have a vector W, which has components W sub 1 and W sub 2. Then the dot product of those two, U dot product W, dot product of U and W, is going to be U sub 1 times W sub 1 plus U sub 2 times W sub 2. Okay, so I had a quick little break there, and we have the mystery of the barking dog solved, hopefully. And we're going to go ahead and do some examples of dot products with these three vectors. I have just made over them. Usually they do when we write them by hand. When you see them in a textbook or in sort of printed media, which you might see visually online, you see them in bold or italicized print, usually, just the name of the vector. So don't be thrown too much by that. Okay, so if I want to do the dot product of U and V, that means I'm going to multiply 4 times 7, and then I'm going to add to that the product of negative 6 and 2. So I've got 4 times 7 plus negative 6 times 2, that's 28 minus 12, which is 16. So the dot product is a single number. When you get your answer, it is one number answer. And I don't mean one digit, but it's just a number. It's not a sum of numbers. It doesn't have I's and J's on it. It's just a number. All right. Another way of thinking of this, remember, we could think of those as being written in this form. And this is what we call component form. And this is the same thing. I just think in some ways it makes it a little bit more clear because it boils down to what are the things that we're going to deal with, those coefficients, 4 times 7 plus negative 6 times 2. Okay, let's try V, the dot product of V and W now. So V, the coefficient of I is 7, and for W, the coefficient of I is negative 3. So I'll start out with 7 times negative 3 plus, and then for J, the coefficient of J is 2, and the coefficient of J for W is negative 1, so 2 times negative 1. Okay, and let me just point out to you with dot products, it's possible for you to have three components. You could be in 3D, in a 3D coordinate space, basically. And then you do these two together, and then add the product of these two together, and then add and do the product of your third components, or your third directions. Well, they're really components too. But here we only have two, and we're going to go ahead and put these together, and we come up with negative 23. All right, and if we wrote W in component form, that would be negative 3, negative 1. Okay, now sometimes you only have an I or you only have a J, and if that's the case, you would treat the other letter, the letter that you don't see, as just having a 0 in front. Like if this just said 3I, negative 3I, then I would consider that negative 3I plus 0J, and I'd have a 0 right here. All right, we can take the dot product of a vector with itself. So V and itself. Remember the vector V has components 7 and 2. So this is 7 times 7 plus 2 times 2. 7 times 7 is 49, 2 times 2 is 4, and that's 53. All right, next I wanted to get a little bit fancier, just a tiny bit. And this is the product of a scalar and a dot product. Okay, where a scalar, remember, is just a number that's being multiplied times everything. It's kind of like it's scaling it 3 times as large. It's changing the scale of the whole thing, is why we call it that. So first I need to do the dot product of u and w. So the dot product of u and w is 4, let's come back up here, 4 times negative 3 plus negative 6 times negative 1. Okay, so 4 times negative 3 plus negative 6 times negative 1. And that's negative 12 plus 6, which is negative 6. And then I'm just going to multiply that times 3. That's just been sort of hanging out front, waiting for me to be done simplifying my dot product. And there's my answer. All right, on number 5, these parentheses are telling me I need to add this first. Okay, so I'm going to go ahead and take care of that. I'm adding the sum of vectors u and w. Well, once again, to do a sum or a difference, we would just pretty much use our coefficients. So u and w, the sum of u and w, so that's 4i's plus negative 3i's, that's going to be 1i. Negative 6j's plus negative 1j is negative 7j's. So the sum of u and w, 4i minus 3i was 1i. Negative 6j's and negative 1 more j is negative 7j's. Okay, so I want to do the dot product of v with this vector. Okay, so the vector v I can represent as 7i plus 2j. So I'm doing the dot product of those. So I'm going to do the 7 times the 1 plus the 2 times the negative 7. 7 times 1 plus 2 times negative 7, which is 7 minus 14, which is negative 7. And that is my answer. So those are all just basically doing the calculations to find the dot product. Now, one of the first things we do with dot product usually is use it to find out if two vectors are something called orthogonal. All right, the word orthogonal is spelled, as you can see here, O-R-T-H-O-G-O-N-A-L. And basically, it's just a sort of a special case word for perpendicular. That's the best way to think of it. There are, if you try to like Google it, or depending on what your textbook is that you're working with, there are different minor distinctions that people will use to talk about why we would sometimes use the word orthogonal and sometimes use the word perpendicular. But for the most part, it's really nothing that you need to even worry about there being a difference. Pretty much vectors that are orthogonal are vectors that meet at a right angle. So now here's the cool thing. Determining whether or not the vectors are orthogonal is a very simple process. It uses the dot product, and it basically is if the dot product is equal to 0, then the vectors are orthogonal. Okay, so another way to we'll write that in symbolism. If we have this, then let's say if, then u and w are orthogonal. Orthogonal. Squeeze it in there. Yeah, that's really rough. Sorry. Okay, so basically, if we're asked to find out whether vectors are orthogonal or not, we're just basically being asked to find out whether their dot product is 0. So it's a yes or no. If I do the dot product and I get 0, then yes, they're orthogonal. If I do the dot product and I don't get 0, then no. So here my dot product is 8 times negative 6 plus negative 4 times negative 12. Please be very careful with your signs on these. That's the easiest place to mess up. Pretty much just like any other math, honestly. Negative 48 plus 48, that's 0. Yes, they are orthogonal. Okay, if you graphed these two vectors on the coordinate plane, they'd look perpendicular. That's what it means. All right, next, number 2. Are V and W orthogonal? Well, I have to check by doing their dot products, or their dot product. Sorry, single. So 5 times, this is a 1, an imaginary 1, and this is imaginary 1 behind the negative. So I've got 5 times 1 plus negative 5 times negative 1. So that's 5 plus 5. So that's 10. So no, those are not orthogonal. Finally, here's one where we just have one letter. So remember that if I have 3i, that means 3i plus 0j's. And if I have, that's supposed to be a negative 4j, my negative kind of had to get squeezed in there. If I have negative 4j, that means I have 0 i's and I have negative 4j's. So that's what I've got here. So if I want to know if V and W are orthogonal, I'm going to find their dot product, and that's 3 times 0 plus 0 times negative 4. 0 plus 0 is 0, so yes, those two vectors are orthogonal. All right, so then one of the next things we would tend to look at after finding out whether or not two vectors are orthogonal is thinking a little bit more broadly and looking at two vectors and saying, well, are they orthogonal, are they parallel, or are they neither one? So let's look at what it takes to be parallel. We know that to be orthogonal means their dot product is 0. To be parallel, basically, one of them has to be a product of the other. Okay, here's what I mean. That basically I can take either one of the vectors and say if I multiply the other, oh, that's equals, sorry, equals, if I multiply the other vector by some random scalar. So let's just use k. K times w. Meaning a scalar, meaning remember we said we were scaling things up by a factor of 3 times as large. So basically one number times all of it. Like one of them is 12 times as big as the other, exactly 12. Both the horizontal and the vertical components are exactly 12 times as big, so k would be 12. Or one of them is negative 2 times as big as the other. Or one of them is 0.5 or 3/5 times the other. It doesn't have to be an integer. So let's just look at this. Number 1. Parallel is really the easiest thing to check first. So that's what I'm going to do. I'm going to look at, let's just look at the horizontal components to begin with, and see if one of them seems to be a product of the other. Now, really, you can just say always that there would be, yes, if I multiply one of them times something, I'm going to get the other. It might be times 7/5 or something like that. So then the key thing is whatever I would multiply this by to get this, could I multiply this by the same number and get this? Okay, so another way of thinking about that is the ratio of your x values or your horizontal values and sort of a values really here, is that the same as the ratio of your vertical values? Meaning, is 5 over 10 the same as negative 2 over negative 4? Yes, they're both 1/2. So that tells me, yes, these are parallel. There is some number that I can multiply one of the vectors by and get the other one. And in this case, I'd say that would be W is 2 times V. Or I could go the other way and I could say that V is 1/2 of W. So yes, these are parallel. Because whatever you would have to multiply your coefficients of I by, remember this is like AI minus B. Okay, whatever your A's, multiply this A by to get this A. I'm going to go ahead and say this plus. I would have to do the same thing with B to get this B. All right, so let's look at this one. To go from 2i to 4i, this is twice as big. 2 times 2 makes 4. So does 2 times negative 7 equal 11? No. So these are not parallel. And you might have to explain that. Very often you don't. But you could say 2 over 4 is not the same as negative 7 over 11. That tells me there's nothing that I can multiply the first one by in both horizontal and vertical components that would give me the second one. All right, so the next thing I'm going to check is, because I'm being asked all three things here, parallel, orthogonal, or neither. And there's not a special test for neither. It's just if it's not one of these two, then we call it neither. Or neither, depending on the way you like to pronounce that. So I'm going to do the dot product to see if maybe these are orthogonal. Okay, my dot product 2 times 4 plus negative 7 times 11. It becomes pretty apparent pretty quickly that that is not going to be equal to 0. It really doesn't even matter what it is equal to, but it's going to be equal to, I think, negative 69. This is not 0, so they are not orthogonal. So this is a neither. Or neither. And finally, number 3. When I look at this, I think, okay, what can I multiply 5 by to get 9? Well, that would be 9/5. So if I multiply 8 times 9/5, would I get this? No. This is not going to be parallel. You could also check it. If you weren't sure, if the numbers weren't easy to tell, you could check it several different ways to check whether two proportions are the same. You can cross multiply and see if you get the same thing multiplying this times this as you would this times this. You can put them both in your calculator as a division problem, 5 divided by 9, negative 8 divided by 45/8, and make sure you get the exact same thing. And I mean exact same thing, like to the 4th and 5th and 6th and 7th decimal place, not rounded. Or you can change them to simplified fraction form and make sure you get the exact same simplified fraction when you take it to the most basic fraction you can make of it. But any which way you slice it, these don't work. So these are not parallel. And now I'm going to check and see if they're orthogonal by finding their dot product. We've got 5 times 9 minus 8 times 45/8. One thing I love about it when they give us problems where they throw a fraction in at you out of nowhere, and you're like, oh, boy, maybe that would be easier if I changed it to a decimal. 9 times out of 10, no, it wouldn't, because they're going to give you a situation like this. That cross cancels. That's just 45. It would be a whole lot harder to deal with if we had changed that to a decimal. And yes, they are orthogonal because their dot product is 0. Remember, that's our criteria. Okay, I've got one last thing to show you. Kind of, you can think of it as a bonus problem. And it's just a problem you might be asked about. That kind of just checks that you know what you're doing with orthogonal vectors. So it says find A, the value of A, so that vector V, which consists of I minus AJ, and vector W, which can be represented as 3I minus 8J, are orthogonal. Okay, so to make them orthogonal, remember the whole key is that our dot product has to be 0. So I kind of have to define my dot product here. My dot product, I'm going to go ahead and put a 1 here. 1 times 3 plus, and I'm going to go ahead and make sure I take this minus as a negative with my A, negative A times negative 8. It's like a negative 1A. So this is 3 plus 8A, and we said it has to equal what? It has to equal 0 to be orthogonal. So I'm going to subtract 3 from both sides. I get that 8A has to equal negative 3 for this to happen, which means that A has to be negative 3/8. And that's my answer. I hope this has helped and you are much more confident about dot products of vectors and what it means to be orthogonal and how you can use that and find that out. Thanks so much for coming, and I hope to see you in the next video. And meanwhile, enjoy math. Bye-bye.